So, this will be the last lecture of module 5, and in this lecture I will first of module 8, and in this lecture I will first recap what we have done in module 8, okay, and then we will discuss some practice problems. So, let us see what all we learnt in this module. In this module we basically learnt about Fourier series and about orthogonal eigenfunction expansion. So, in the first lecture we discussed Fourier series and Fourier expansions. Okay, we saw how we can write a function in terms of its Fourier series. We saw what a Fourier series is. Then we looked more at Fourier expansions. We looked at various functions and what their Fourier expansions look like, and then we also saw how to solve differential equations using Fourier expansions. This part I should emphasize is something that is very useful. We will not be doing practice problems on this, because this is especially useful in numerical solutions of differential equations. Then in the next lecture we saw orthogonal eigenfunctions and the Sturm-Liouville theory. So, there were only 3 lectures, because some of these lectures were a little longer. So, we saw the Sturm-Liouville theory and how to analyze in terms of orthogonal eigenfunctions. So, today I will do some practice problems. Now, this material is explained very nicely in Macquarie in chapter 14 and 15, and Kreyszig has some discussion on these things, and part of Sturm-Liouville theory is there in chapter 4, and then Fourier series is discussed in chapter 10, where actually partial differential equations are discussed. But again, I should emphasize that these books have a lot more than what we are doing, okay, but nevertheless they are useful references. Okay. So, now let us go and start working out a few practice problems. So, the first problem, this is a quantum mechanical free particle problem, and this gives the idea of plane waves. The problem is, consider a free particle in 1D. The Schrodinger equation, the time independent Schrodinger equation for this particle is given by this, okay, minus h cross square by 2m d square by dx square psi x equal to E psi of x. Solve for psi of x for different values of E such that E is greater than 0. Okay. Then the next part is to consider periodic boundary conditions psi 0 equal to psi L, psi prime of 0 equal to psi prime of L, and you write this as a periodic Sturm-Liouville problem. Okay. Calculate eigenvalues and eigenfunctions and verify orthogonality. Let us solve this. So, the first part is to do the free particle. Okay. So, the free particle part, okay. So, this is the free particle. Okay. So, the free particle part, I can just write this out. This is a simple second order differential equation. So, I can write d square psi by dx square is equal to minus 2me by h cross square psi. So, I can write as psi of x as constant. I will just write a e to the I, okay, and you have square root of 2me by h cross square times x. Okay. And I'll use the notation. I'll write this as and it can be either plus or minus. Both the solutions are valid. Okay, so it can be plus or minus. Now I'll write this as a e to the plus minus I k x, where k is equal to square root of 2me by h cross square. E is greater than 0. Okay, so this is the square root of that. So, now this is a solution for E greater than 0. So, the general solution psi of x is equal to a e to the I k x plus b e to the minus I k x. So, e to the k x, e to the I k x and e to the minus I k x are linearly independent functions. Okay. So, you can write the general solution as a linear combination of these. Alternatively, or you can write psi of x as a sin k x plus be cos kx. So, if you do not want to deal with sines and cosines, you can also write in, if you do not want to deal with imaginary functions, you can also write in this form. You can easily verify that sine and cosine will also satisfy this equation. Okay. So, that is the first part, okay, where you solve for different values of E such that E is greater than 0. Now, I consider the periodic boundary conditions. So, psi of 0 equal to psi of L and psi prime of 0 equal to psi prime of L. Okay. So, now if I take this differential equation, so let me take this h cross square by 2m to the right. So, I will write equal to 0. So, I can or I can write this as x square. Let me just write this as 1 d psi by dx, the whole thing prime, okay, or just to keep the notation short, I will just write psi prime plus 0 plus 2 m e by h cross square psi equal to 0. Okay, I wrote it in this form. You can immediately see that p of x is equal to 1, which is greater than or equal to 0, q of x equal to 0, which is again greater than or equal to 0, r of x equal to 1, lambda is equal to 2 m e by h cross square. So this now we also notice that since psi of 0 equal to psi of L, okay, this is by demand, we have demanded this, okay, and psi of prime of 0 equal to psi prime of L. Okay. Now, we notice that p of 0 equal to p of L equal to 1. Okay. So, this is a periodic. So, actually just by this equation, okay, we can look for solutions that satisfy this. Okay. So, this is a periodic Sturm Liouville problem. Okay. This is a Sturm Liouville equation, and this is these boundary conditions imply that it is a periodic Sturm Liouville problem. Okay. So, what that means is that you can have solutions. Okay. So, the lambda equal to 2 m e by h cross square is real. Okay. So, you can have various solutions. Okay. You can have various solutions. So, you can have solutions psi lambda of x corresponding to eigenvalue lambda, and basically each you can have different values of E, okay, and each of those will be orthogonal. You need your psi lambda of x to satisfy the boundary conditions. Now, we saw that in general we have you can write psi of x in this form. Kx. So now psi 0 equal to psi L implies a plus b is equal to a e raised to I k L plus b e raised to minus I k L, and psi prime of 0 equal to psi prime of L implies I k times a minus b is equal to I k times a e raised to I k L minus b e raised to minus I k L. So, these are the two conditions that should be satisfied, and so if I just cancel this, I will get a minus b is equal to a e raised to I k L minus b e raised to minus I k L. Okay. And if I add these two, what I will get is that I will get 2 a is equal to 2 a e raised to I k L. Okay. This implies e raised to I k L is equal to 1, implies k is equal to 2 n pi by L. So, the solutions, so now instead of k, so use n instead of k, okay, and you can write psi n of x is equal to a e raised to I 2 pi by L n x, okay, and your orthogonality relation implies integral 0 to L psi n of x psi m of x dx equal to 0 if n is not equal to m, and this can be easily verified. This is easily verified. It is nothing but a Fourier series. Okay, so this is nothing but a Fourier series, because these are just the coefficients in a Fourier expansion. Okay, and so you can easily verify these. Now, these functions are referred to as plane waves. Okay. Now, if I take different values of n, okay, then I will get different functions. Now, all these functions are periodic in the interval 0 to L. So, if I plot them, okay, 0 and L, okay, these will be periodic functions. So, whatever the value is at 0, okay, you will have the same value. So, you might have you will have both the real and imaginary parts of this function be periodic. Okay, so, for example, if you look at the real part is cosine. So, what it will look like is it's a cosine with this period. So, it will look like this. This is for n equal to 1. Okay, n equal to 2. It will look again like a cosine. So, this is the real part of psi. N equal to 2, it will again look like a cosine, but it will have a different period. So, it will have this is n equal to 2. So, n equal to 1 looks like this, n equal to 2, let me show in blue, n equal to 2. So, if n equal to 2, then it will look n equal to 2 and so on. Okay, and you can easily verify that each of these are orthogonal. Okay, so, these are plane waves that with this periodicity of L. This is a very useful way of writing solutions for wave functions of solids. Okay, so, for periodic solids or periodic systems, and solid wave, the wave function in a solid is expressed as a linear combination of plane waves. Okay, and we showed a one dimensional plane wave. By taking product of plane waves in different directions, we can construct 3-dimensional plane wave. So, we can multiply a plane wave in x by a plane wave in y by a plane wave in z, and these are 3 independent directions. So, you can get these 3-dimensional plane waves. Okay. Now, the next problem, okay, this is another very practical application of orthogonal eigenfunctions. Okay. So, this is in deriving spectroscopic selection rules from orthogonality of eigenfunctions and recursion relations. So, the dipole selection rule, okay, is one of the most commonly used selection rule, okay, in spectroscopy. So, this is based on the transition dipole moment integral. So, this integral is you take a wave function, okay, multiplied by x, okay, and you multiply it by another wave function, where x is basically some I mean you can think of x as some coordinate. It might be a spatial coordinate, it might also be an angular coordinate. For vibrational spectroscopy, okay, psi v of x, the wave function, is indexed by a quantum number v. Okay, so, v is the vibrational quantum number and equal to 0, 1, 2 and so on, and this function is given by h v. This is the Hermite polynomial. So, it is a Hermite polynomial multiplied by this exponential function by this Gaussian function e to the minus x square by 2. Okay, this is called a Gaussian function. Okay, so HV of x is the Hermite polynomial, and the Hermite polynomial satisfies a recursion relation. Now, the recursion relation says that h of n plus 1 corresponding to n plus 1 Hermite polynomial, okay, minus 2 x into h n, the nth Hermite polynomial, plus 2 n into h n minus 1. So, the n plus 1 nth and n minus 1th Hermite polynomial are related by this recursion relation. And what we have to do is to use this to derive the selection rule for vibrational spectroscopy. Now, to solve this, this is not very difficult, you just take this integral. Okay, so, let us write this integral. So, the transition dipole moment, so integral psi n psi v of x, x psi v prime of x dx from minus infinity to plus infinity. This is a range of x, okay, for a Hermite polynomial or for the vibrational quantum number. This is equal to integral, okay, now I can write this as h v of x e to the minus x square by 2 times x times h v prime of x e to the minus x square by 2 dx from minus infinity to plus infinity. Now, I cannot use any orthogonality relation because I have an x here. So, let me write this out in the following form. I should mention that there should be a complex conjugate here. Now, these are real functions. So, the complex conjugate is nothing but the function itself. So, let us just go ahead and write this out. Okay. So, this is equal to integral minus infinity to plus infinity. Now, what we have is h v of x, x h v prime of x e to the minus x square dx. Now, what we will do is we will take this x, we will take x times h v prime of x, okay. We will use the recursion relation, okay, in the following form. So, if you rewrite this, what you can show is that this is equal to half integral minus infinity to plus infinity h v of x. Now, I take the x h n on the right, okay. So, I will get h v plus 1 of x plus 2 v or v prime plus 1, 2 v prime h v prime minus 1 of x, and then I have e to the minus x square dx. So, I took the half factor down. So, what you get is that you will get two terms. Okay, so, the first term is half integral minus infinity to plus infinity h v of x h v prime plus 1 of x e to the minus x square dx plus integral, I have a v prime, I will just take the v prime outside, okay, it is independent of x, and what I have is h v of x h v prime minus 1 of x e to the minus x square dx. Okay, so, you have these two terms. Okay. Now, using the orthogonality of Hermite polynomials, okay, so this is equal to 0 unless v equal to v prime plus 1. So, the first term goes to 0 unless v equal to v prime plus 1, second term goes to 0 unless v equal to v prime minus 1. This equal to 0 unless v equal to v prime plus 1 or v equal to v prime minus 1. Okay. So, the selection rule, okay, so I can write v minus v prime is equal to plus minus 1. This is the selection rule. Okay. So, this is the selection rule for vibrational spectroscopy. So, under the harmonic oscillator approximation, okay, your vibrational spectroscopy, okay, you will not have a vibrational spectrum, okay, so this transition dipole moment integral, okay. So this will be equal to 0 unless you have this condition. So if you do not have this condition, you will not have any spectrum. So if this transition dipole moment goes to 0, then there is no spectrum. So the condition for having a spectrum is that your V minus V prime should be plus minus 1, or the difference between these two states n and m, okay, should be that their vibrational quantum number should be either they should differ by 1. Okay. So this is a very practical use of or a very commonly used a very common application of these orthogonal eigenfunctions. Okay. So next problem is the Legendre equation and rotational spectroscopy. So we'll do it in various steps, this problem. So the first step is to write the Legendre differential equation, which is given by 1 minus x square y double prime minus 2 x y prime plus n plus 1 y equal to 0 as a Sturm Liouville problem. The second part has to do with the quantum mechanical rigid rotor wave function, and this is given by spherical harmonics. So spherical harmonics, so there are two quantum numbers L and m. Okay. So YLM of theta and phi are the angular coordinates. This is given by, this is called an associated Legendre polynomial PLM of cos theta, absolute value of m of cos theta is an associated Legendre polynomial. Okay. It is a function of cos theta, and this satisfies. So if the variable was x, then this PLM would satisfy this equation. Okay. So it looks like a Legendre differential equation, 1 minus x square p double prime of x minus 2 x p prime of x. Okay. So which is exactly the same as these two terms, and then plus L plus 1, which is again very similar to the Legendre equation, but you have an additional term m square over 1 minus x square px. Okay. So it only slightly differs from the Legendre differential equation, and therefore this solution is called the associated Legendre polynomial. Now what I am asking you to do is, for fixed m, write as a Sturm Liouville problem and derive the orthogonality relation, which is fairly straightforward. And then the last part is to use the recursion relation. Okay. So the associated Legendre polynomials, they satisfy this recursion relation. So 2l plus 1 x into PLM of x, okay, minus L minus absolute value of m plus 1 times PL plus 1 L plus 1. So instead of L, I had L plus 1. I always have m everywhere. Okay. And in the last term I have L minus 1, and you use this to derive the spectroscopic selection rule for rotational spectroscopy. Now you can see that the last part will be exactly the same as we did for the vibrational spectroscopy. So let us first write the Legendre differential equation as a Sturm Liouville problem. So to do this, so if I take 1 minus x square y prime the whole prime, okay, this is equal to 1 minus x square y double prime minus 2x y prime. So I can write the Legendre differential equation as 1 minus x square y prime the whole prime plus 0 plus n plus 1 times 1 times y equal to 0. So this is a Sturm Liouville problem. P of x is equal to 1 minus x square, q of x equal to 0, r of x equal to 1, lambda equal to n plus 1. Now we see that p of x is greater than equal to 0 if x is less if x square is less than equal to 1, or minus 1 less than x less than equal to x less than equal to 1. And we also notice that p of 1 equal to p of minus 1 equal to 0. Okay. So therefore I can write this as, so this is so no need for boundary condition at 1 and minus 1, and I can write the orthogonality relation as minus 1 to 1. Okay. Now if the solutions okay, for a given value of n, okay, are denoted as Pn of x, Pm of x dx equal to 0 if n is not equal to m. Okay. So this is how you can write the Legendre equation as a Sturm Liouville problem. Notice that I am using n, okay, instead of lambda. okay, but that does not matter. You know that n plus 1 is nothing but lambda. So, lambda is n plus 1, okay, and p of x is 1 minus x square. Okay. Your weight function r of x is equal to 1. Okay. So, I do not need to have any weight function here. Okay. So, this shows how you can write various equations as term level problems. Okay. Now, let us look at the next part. Next part is to take this equation for the associated Legendre polynomial. So, for the associated Legendre polynomial, now I can do exactly the same thing as I did before. So, I can write 1 minus x square y prime, the whole thing prime, plus my q in this case is m, I can write as minus m square over 1 minus x square, and plus L plus 1 y equal to 0. Okay. So, now remember the Sturm Liouville problem conditions. Okay. So, if you go back to the previous lecture. Okay. So, the Sturm Liouville problem conditions, the Sturm Liouville problem condition, the condition is that p should be greater than or equal to 0, r of x should be greater than or equal to 0. There is no condition on q can be anything. Okay. So, in this case q is actually negative. So, what we identify is that p of x equal to 1 minus x square, q of x equal to minus m square over 1 minus x square, r of x is equal to 1, lambda equal to L plus 1, and we can immediately write the solutions. So, again we have p of 0 p of 1 equal to p of minus 1 equal to 0. So, we can write the orthogonality condition as before. P L m of x, P L prime m of x dx equal to 0. This is for a given value of L, for a given value of m, for fixed m. So, that is the orthogonality relation, and this completes the second part. Now, the last part is to use the recursion relation for P to derive spectroscopic rules for rotational spectroscopy. Now, in this case your transition dipole moment okay, so that will look like y phi, and then now actually there is a term that looks like cos theta, okay, and I have y L prime m prime of theta phi integral, and the integral is over sin theta d theta d phi. Okay. So, this is what this integral looks like, and there are two limits are from d theta goes from 0 to pi, d phi goes from 0 to 2 pi. So, this sin theta d phi is the Jacobian, okay, for in this for converting to spherical polar coordinates. So, we are converting to these angles theta and phi. So, this is what your transition dipole moment looks like. Now, you can clearly see that if I expand for y L m of theta phi, okay, if I write this y L m of theta phi in terms of a theta part, that is p L m cos theta and e to the I m phi, okay, then what I can see is that the phi integral 0 to 2 pi, the phi integral, the integral over phi will just have e to the I m phi e to the, and I should put a complex conjugate here, e to the minus I m phi, okay, times e to the plus I m prime phi. So, the minus came because you took a complex conjugate d phi, and then I have a theta integral that looks like integral 0 to pi, and what I have is p L m cos theta times cos theta L prime m prime cos theta sin theta d theta. What you can see from the first integral is that this looks like integral 0 to 2 pi e to the I m minus m prime phi d phi, okay. And this equal to 0 unless m equal to m prime. So, if m is not equal to m prime, then you can easily show that this goes to 0, okay. So, that is the first one, okay. So, the first integral is just this, okay. So, therefore, what we will say is that m equal to m prime is one condition or selection rule. Now, the second condition we can get by putting m equal to m prime in this, what you will get is and then you will put x equal to cos theta, dx equal to minus sin theta d theta x. So, what I will get is, so this second integral. So, integral over theta becomes integral. Now, when theta equal to 0, x equal to 1, theta equal to pi, x equal to minus 1. Now, I have P L m of x times cos theta is x, and I have P L prime m prime of x. Now, sin theta d theta, theta is minus dx, So, what I can do is I can just change the limits and I can write this as P L m of x, P L prime m of x dx from minus 1 to 1. Now, we already saw, okay. So, now let us use the recursion relation. So, using this recursion relation, so the recursion relation says that 2l plus 1 times x P L, okay, is given by some quantity L minus m minus 1 P L plus 1 and some constant times P L minus 1. Okay. We can replace this, okay, by two terms, one that involves P L prime plus 1 and another that involves P L prime minus 1 of m, okay. And use orthogonality just like Hermite polynomials, L equal to L prime plus 1 or L equal to L prime minus 1. So, for non-zero integral. So, unless L equal to L prime plus 1 or L equal to L prime minus 1, your integral will be non-zero. So, the final selection rules for rotational spectroscopy, m equal to m prime, L equal to L prime plus minus 1. So, what I have shown you through these problems, okay, this is again very useful selection rule for rotational spectroscopy. So, we can see the applications of this orthogonal eigenfunctions, okay, in actually deriving selection rules for spectroscopy. Okay. So, I will conclude this module on module 8 with this, and next week we will start module 9. Thank you.